Welcome back to the series on design patterns. Today we are going to talk about the difference between Decorator Pattern and Composite Pattern. So the Decorator Pattern we've already talked about in another specific video, and the Composite Pattern we've already talked about in another specific video. But in this video I want to talk about the sort of nuances, and I want to talk about the differences between these, because actually if you look at them, they look very, very much the same. But hopefully, since they have two different names, they should turn out to be two different patterns. And also, by the way, if you're new to this channel or to this playlist, let me just mention that this is a playlist where we talk about all of the famous design patterns. So we've already talked about tons of design patterns. Check out the playlist if you want to see any of those. And we have tons left to go, so subscribe so that you won't miss these. Anyways, I did a bit of Googling to try to figure out the sort of differences between Decorator and Composite Pattern. And it's not super clear, and people have sort of different arguments for the differences. And a lot of the times it comes down to intent, so the reason for using that particular pattern. And then we often end up in the discussion of the composite pattern is useful when you have a structure that by its very nature is hierarchical, or you have some piece of data that is susceptible to being modeled hierarchically in a sensible fashion or usefully. Whereas when we talk about decorator pattern, we have situations where we want to be able to, at runtime, alter the behavior of some particular thing. So an object is passed around in your application, and at runtime you want to be able to change that particular thing or change the behavior of that particular thing without actually opening up the class and altering it. So it's a way of supporting the open-closed principle from the solid object-oriented design principles. If you want to know more about the solid design principles, check out the link in the description for a playlist on that. Hopefully this will be a very short video. I want to do three things. First, let's read the definitions of both of the patterns. Then let's look at both of the UML diagrams side by side. And then third, let's talk about what in my mind seems to be like the key difference between composite and decorator, or at least the one that I find the most interesting. Let's get started. So I'll read the definitions from this book. Design patterns, elements of reusable object-oriented software. It's like the classic design patterns book by Gang of Four, which essentially means there are four authors and they're usually denoted as the Gang of Four. Super good book, by the way, if you want to know more about design patterns. Yes, we cover a lot of stuff in this playlist, but clearly there's a lot of more information in this book. And also, if you want something more pedagogical, maybe get this book. This book has more pictures and more funny jokes and all that. Head first, design patterns. This book also has examples in Java, so also that makes it a bit more accessible. Links to both of these books are in the description. Moving on. But let's now read the definitions. Let's start with composite pattern. So, composite pattern composes objects into tree structures to represent part-whole hierarchies. Composite lets clients treat individual objects and compositions of objects uniformly. So we're not going to dig into these definitions in details because, as said before, there are specific videos for both of these patterns. So check out the links in the description for specific videos to these patterns. But anyways, just very quickly, composite pattern is, as we were saying before, helpful when you have data that is modelable as a hierarchy. And the key point here is this last sentence. Composite lets clients, in other words, the user of your code structured within the composite design pattern, the user of that code, you let that person or that code base treat your objects and compositions of objects uniformly. And if you have a look at the composition pattern video, what we talk a bit about there is that this lets you eliminate an if-else branching. So if you think about Martin Fowler's book Refactoring, there's this refactoring that he calls replace conditional with polymorphism. Essentially, that's what happens in composite pattern. If you have a tree of things, then some things have some things and other things are leaves. Other things are in the end of the hierarchy. Let's just look at it this way. If you have a tree of things, this thing, and this thing, they all have subnodes. But these things in the bottom, these don't have subnodes. So they are fundamentally, qualitatively different from these nodes above, from these parent nodes that do have children. So if you didn't use composite pattern, you would probably use an if-else statement so that when you run an algorithm, your algorithm would do one thing here and another thing here. In other words, One thing if it's in a node that has children, and another thing if it's in a node that doesn't have children. And that's the conditional I'm talking about. So when we use composite pattern, we replace that conditional with polymorphism. And that's what we achieve through composite pattern. But anyways, now to the decorator pattern. So the definition of the decorator pattern, again from the same book, the decorator pattern attaches additional responsibilities to an object dynamically. Decorators provide a flexible alternative to subclassing for extending functionality. So this is a totally different story, right? If you go back to intent, if we go back to why you would use this pattern. So this pattern is trying to describe a situation to us where we have some kind of object and we want to be able to change the behavior of that object at runtime. Or more specifically, in their words, we want to be able to attach responsibilities. We want it to be able to do more things, but we want to be able to do that dynamically. So we don't want to open up the class and change the class. So we want to do it at runtime, but we don't want to do it using subclassing. So we don't want to introduce another subclass because we want to have that compositionality. We want to be able to mix and match different behaviors or different responsibilities. So this is a totally different story. But we'll get into this in more detail. Before we move any further, let's first look at the UML diagrams of both of them. So let me remove this stuff. Let's just add a divider here. Let's say that composite is here and decorator is here. And now let's draw the UML diagrams. So composite looks like this. You've got a component, and actually I'll do a very simplified version of UML just to save everyone's time. I mean, usually you draw this line here and then you add the public interface of that class. But again, since all of that information is in the other composite pattern video and in the decorator pattern video, please check out those if you want more details. But now we just want to sort of glance at the high level structure of these two patterns. Like the question we're asking ourselves is, are they structurally fundamentally different or are they actually the same? Right? Because, I mean, intent can vary, fine, but it might be that intent varies and then they are exactly the same, right? Then it's only intent, but maybe it's also structure, and that's what we're looking at now. So, we start off with a component, and the component interface is implemented by two classes, the leaf and the composite. And the composite aggregates components. The key portion here is, let me say, one, two, many. So again, without going into too much depth, you have something which is called a component, and both leaves and composites are components. But leaves are essentially the end of the tree. If you think about a tree, you have a parent, and then you have subnodes and subnodes. So in other words, you have a node that has two children, and then these two children have two children of their own. And then you can continue in this way indefinitely. When you get to the bottom, these nodes in the bottom, these are leaves, because they don't have subsequent children. All other nodes are parents. So all other nodes are composites, but these nodes in the end, they are leaves. So composites have components, and this is how we get into this sort of recursion, where a leaf and a composite both are components, but composites have references to other components. And since components can be components, you can build an infinitely deep tree, theoretically. Now let's draw the decorator. So the decorator, however, also starts with a component. Component. Let me just remove this line for clarity. So it also starts with a component, and it also has these two subclasses or implementors of the interface, where this one we call a concrete component, and this one we call a decorator. And then the interesting portion is that the decorator aggregates components. And at this point, this is probably where you're feeling, wait, okay, these are actually literally the same diagram except for the texts. Literally, except also for this thing. By the way, they don't draw, so this is known as multiplicity. In other words, when I said one to many, this is known as multiplicity. So a composite can have components, but the question is how many components can it have? What's the least amount that it needs to have, and what's the maximum amount that it can have? So this is multiplicity. So I actually added this notion of the multiplicity. I'm not sure in the Head First book, but surely in this Design Patterns book, the Gang of Four book, they don't actually draw out the multiplicity, or they don't actually specify the multiplicity. I don't know, sometimes it's done in UML, sometimes it's not. So anyways, I mean, if you just take these portions at face value and you ignore this part that I added, they are literally the same, these diagrams. Again, except for the texts. But I added this notion of the multiplicity in the composite because that's what we're doing with the composite. But here's where we get into the subjective parts, where I'm interpreting what the actual intent of this pattern was, or the intended structure. Anyways, but that's not all, right? Because so far they're exactly the same. But actually decorator is slightly different because there's a continuation here. So the next step is that this decorator is also inherited from or implemented if it's an interface. And I'll draw this sort of leaf on leaf notation. Here I don't mean leaf as in leaf from the composite, I mean leaf as in paper leaf. So I'm trying to, in a 3D way, draw that you have two different classes on top of each other, just to emphasize that we can have multiple implementers of the decorator interface. Clearly, I mean, anytime you have multiple, or anytime you have inheritance or interface implementation like this, you can have multiples. But just when we're drawing this, I'm trying to emphasize that the intention is that this would completely vary based on your scenario, and in your scenario you might end up with 2 decorators or 200 decorators. Both are valid in terms of the decorator pattern. So this is just what I'm trying to denote here. You might want multiple decorators, but I'll only draw one because of, I mean, there's no point in me drawing multiple ones for everyone's time. So what do we call this? Well, this we call a concrete decorator, which sort of suggests to us that if this is a concrete decorator, then this decorator class ought to be an abstract decorator. Similarly, if this is a concrete component, then this ought to be an abstract component. And now you can see that they're actually different. But, I mean, they're not hugely different, right? If you just think about it, the only thing that's different now is that the class here, in some sense, is the same class as here, right? In the decorator pattern, we call it the decorator. And in the composite pattern, we call it the composite. Because both of these inherit from the main component, and both of these have an aggregation relationship with the component. But the difference now is that we've said that, okay, this decorator isn't necessarily concrete, or actually isn't concrete, it's actually abstract, and then there are concretions that inherit from this abstraction, or implement this interface if it's an interface. And that's the difference. Now, I mean, the reason we do this in decorator pattern is, as far as I understand, fairly practical. It's simply because if you have, so maybe before we go there, let's just quickly recap what the decorator pattern does, right? The decorator pattern, with the decorator pattern, you have something, so sorry, I'm drawing at the composite end now, but this belongs to the decorator pattern. So you have an instance of a component, and then you wrap that component with decorators. Right? So all of these outer lines are decorators. Again, please see that other decorator pattern video if you want to dig into more of what this means. But the point is, you have this component in the middle, you have this concretion in the middle, and then you wrap decorators around that concretion in order to attach additional behavior. So that when somebody calls the outer shell of this decorator who decorates a decorator, or decorates a decorator, or decorates a decorator, or decorates a component, when somebody calls that outer shell, the decorators call each other downwards in a chain, and then the value propagates up, which gives every decorator a chance to augment the value or augment the action that the method performs if it's a void method that doesn't return anything. But if you just think about something that returns something, maybe this innermost component just returns the name, and then one of the components capitalizes the name. You know, in other words, make sure that the first letters in the first name and then in the last name are both capital letters, and then maybe another one flips it so it's last name comma first name rather than first name space last name, or something like this, right? So these decorators alter the behavior of that method or attach additional responsibilities, right? If you think about title casing, right, uppercasing the first letters of both of the words, then that's an additional responsibility. One responsibility is to extract the name from wherever you had the name, and the second responsibility is to turn that into a title case string. That's additional behavior. Anyways. Okay, so if we then go back to the discussion around the decorator pattern of why the decorator pattern has this additional thing of concrete decorators inheriting from this decorator instead of just having multiple decorators. So the reason, if you think about it, the decorator here is probably an abstract class. And this abstract class is a component, right? It needs to be a component in order for decorators and concrete components to be interchangeable. But the thing is that when you've instantiated a component and then wrap that with the decorator, when you call the outer decorator, let's say you call the decorated method, then the decorator simply does whatever it needs to do, like it attaches its additional behavior, whatever its computation is, and then passes the call downwards to the component. But for all of the non-decorated methods, it also needs to actually pass those methods down. In other words, if you have a scenario where the component that you have doesn't have just a single method, Instead, if it has multiple methods, but you're only interested in decorating one, then that means that all the decorators need to pass the call to all those other methods downwards in the chain, downwards towards the next decorator, and eventually down to the component. So if I just draw this in two colors, right? Like, let's say that the blue calls are calls to the method that we're intending to decorate, but the green calls are calls to another method that we don't necessarily intend to decorate, but the component still needs to have it. Or you could even view it this way. Maybe some of the decorators decorate it, other decorators simply just pass the message along. Then in this case we'll intercept the call, but in this other case we'll just pass the call. And the reason I'm saying that is that that would be the passing of the call, that would be the responsibility of this abstract decorator class. So in order to not have to redo that work in every concrete decorator, because it's going to be the same work, it's going to be the same, simply just passing the message along to whoever I'm aggregating. So instead of redoing that work, we put that in the decorator so that concrete decorators can focus on only the thing that they actually want to decorate. And that's the reason for introducing that portion. But, I mean, in my view, I would then say that if you have a scenario where you don't have multiple methods and you're actually only decorating one, then this would be somewhat superfluous. Of course, clearly, I missed one responsibility. The other responsibility of the decorator is that since decorators need to wrap something, we clearly need a constructor in the decorator that accepts the thing that it needs to wrap. So it accepts a component that could be another decorator or could be a concrete component. And so the thing that it's wrapping, taking that and assigning it to an instance variable within the decorator, that's a responsibility for a decorator so that we won't have to do it in every concrete decorator. But you know, I mean, again, that could have been done in the concrete decorator. And about that constructor, I mean, you could argue that the same goes for the composite. You could argue. Now check out my Composite Pattern video for more information about that. But the two books that I mentioned before and most of the resources on the internet go the route of talking about adding add and remove methods to the composite. And then maybe you don't have exactly the same problem. But I was suggesting that Composite Pattern should more be understood in terms of a composite accepting a bunch of components through its constructor so that you don't have to mutate the component. Again, please refer to that other video for more information about that. But if you go that route that I'm suggesting, then Composite Pattern becomes very much like Decorator Pattern. I mean, like, if you look at the essence, if you don't look at like all the tiny details, it seems structurally they're actually very, very equivalent. But that leads me to the third and final point that I want to mention in this video. What I actually subjectively find to be the key difference here is that I'm not really finding a lot of places where people suggest that you could have a decorator that decorates multiple components. So remember we talked about multiplicity. This means that the decorator decorates one to one component. In other words, it decorates one and only one component. In other words, a decorator must have a component. In order for it to be a decorator, it must decorate something. Must. But it can only decorate a single thing. Like, it can't decorate two things. That's not a decorator. So if I'm not mistaken, the books I mentioned before and most of the researchers on the net don't necessarily suggest that it has to be one. But like, if you read between the lines, it seems that that's the implicit suggestion. And it seems that nobody's saying that, well, you could have a decorator that decorates multiple components. And the way I read that is that the reason for that is that if you would have a decorator that decorates multiple components, you wouldn't have the decorator pattern, you would have the composite pattern. Because that's what the composite pattern does. Because as soon as your decorator decorates multiple components, you're building a tree. And that's the whole idea behind composite. But again, now we're very much into the notion of, well, should I call it this thing or should I call it this thing? Maybe it's mostly semantic, and depending on your scenario, you might want to call it one thing or the other in order to suggest to other developers what kind of madness you're up to. So let me draw one final thing which I find particularly interesting that hopefully drives this point home. Let me remove this stuff. But let me re-add the divider. And then we have composite here and decorator here. So we already looked at how composite can be thought of as a tree before. But let's draw one up again. So you have a root node that references two children, or rather you have a parent that references two children. Let's say that these two children reference two children, and so forth. I mean, we could go on, but let's not do that. And then, because this is programming, our nodes have references to other nodes. So we need to think about which direction this reference goes into. In other words, if there's a relationship between nodes, which node has a reference to the other node? And clearly here, the direction goes downwards. So the parent has a reference to 2 children, and each of the 2 children have references to 2 children. But we don't have a relationship upwards, or in other words, the children don't have a direct reference upwards to the parents. This is a key point. If we look at the decorator pattern, however, remember that we said that decorators decorate a single component. That means we're not building a tree. What are we building? Well, what we do is that we have a component, and then we wrap that component within something else. And then we wrap that component within something else. And so forth and so forth. And this notation I find is a bit more difficult than when you think about it this way, right? Like when you have a node that's being wrapped by a node that's being wrapped by a node. But in some sense, I mean, this is just exactly the same thing. If you think about it, what I did is just I moved this here, and then I moved this here, and then I moved this here. Or something along those lines. Maybe it makes more sense to just, so if you think about those as layers, right? It's like I had this node, and then that node, and then that node. I'm trying to draw it in 3D where they're sort of layered on top. And then there's a reference between all of these nodes. And then if you keep sort of tilting your head in this sort of 3D notation, you'll end up with this node that references this other node that references this other node. And then you can probably start to see how we end up here. Something along those lines. But question number 1 that we have to ask ourselves about this relationship here is, again, what's the direction of the arrows? Here the direction was down, but in this case the direction is actually up. Let me exemplify. Because, let's do it this way. This node here is the component. That node is the special node, right? Think about it. You have the base node, and then you have the nodes that can have multiple nodes, the wrapping nodes. So this is the base node, and these are all wrapping nodes, decorating nodes. And actually the same analogy holds for composite pattern, because you have leaves, base nodes, and then you have wrapping nodes, which are parents, which are composites. And here, these are the leaf nodes. So in some sense then, these bottom ones are the base nodes, and all of the other nodes, all of the above nodes, are wrapping nodes, are parent nodes, are the sort of decorating nodes. Whereas in the decorator, the top node is the sort of base, normal, base case node, and all of the nodes below are the special wrapping nodes. And this is where it really starts to get interesting. But you might interject and say, but actually, I mean, this is completely silly, because if I would just take this line and draw it in like literally the other direction, if I would just spin it 180 degrees, then the base node would also be in the bottom in the decorator picture, and the arrows would point in the same direction as the composite. So this proves nothing, right? Clearly it doesn't. But here's the reason I drew this in this direction. Hypothetically, you could use the decorator pattern to build a tree, even if you only allow a decorator to decorate a single thing. This would look, maybe, I mean, if I'm just adding another node, this could look something like this. So I'm just adding another node. So if you think about programming, we have a reference to an object. And when we draw these different dots or these different nodes, what we mean, or metaphorically what we're trying to talk about, are references to memory locations, references to objects in memory. So this node is a location in memory. All of these nodes are locations in memory. They're objects in memory. And if you have a reference to that location in memory, if you have a reference to that object, you can pass that reference to multiple places, clearly. So if I instantiate one concrete component, and then I instantiate a decorator and pass the reference to this concrete component to this decorator, so I wrap it. But then what I can do is I can take the same concrete component. So this, I'm not trying to say this is a different concrete component, it's the same concrete component, right? It's the reference to the same memory location, to the same object in memory, but then I wrap it in a different decorator. Let me do it this way to be super explicit. I wrap it in a different decorator. And then let's, again, to be super explicit, let's draw this in the same color. So it's the same inner component, but I've wrapped it in 2 different decorators. And then I can keep doing this. I can wrap this concrete component again in another decorator or in another decorator, but I could also take these aggregations. I could also take this decorator and wrap it in another decorator, and take this other decorator and wrap it in another decorator, which means that we can continue here in this tree. So I wrap again here. And if this black one corresponds to this one, we need another line here. So then we have two decorators around the component here, and we have two decorators around the component here. But they're all referencing the same concrete component. And then we can keep doing this. We can take any of these points, any of these components, and wrap it in another decorator. We can wrap it in two different decorators simultaneously, but create two different variables. So maybe we wrap this in another decorator. And let's, for completion, draw that as well. So that would correspond to, we have the concrete component, and then we have the first decorator, and then we have this second blue decorator. And if I stop thinking about the colors for a moment, you can hopefully see how we can create this tree, this composite tree, from this decorator tree, if we don't think about the direction of the arrows. So here I have, if we express it using the same terms, in the decorator case I have a root node, a parent node with two children, but only the right child has two children, the left child only has one child. So let's add another child to the left child. Actually, let's stay consistent with the coloring, so let's add that like so, and then we can add another example down here that corresponds to that example. So we have the inner component, the concrete component, that's being wrapped by this first green decorator, and then that first green decorator is being wrapped by this second red decorator. And now if you look at this tree and you compare it to this tree, and if you don't think about the direction of the arrows, they're the same. You have a parent with two children where each of the two children have two children. Exactly the same. But the interesting key differences are A, the direction of the arrows. In the decorator, the arrows are pointing upwards, and in the composite, the arrows are pointing downwards. And also B, that if you think about the base case, if you think about recursion, in this tree, the base case is either in the bottom or in the top. So in the decorator pattern, we have the base case here in the top, but in the composite, we have the base case here in the bottom. Now, clearly, in some sense, if you would use decorator pattern as it was intended to be used, I think we should think about the base case as being in the bottom. Because think about it this way. In your code, when you've constructed this structure, when you've constructed this object structure, which object do you have a reference to? Well, in the decorator pattern, since you're decorating, you would have a reference to one of these. And in the composite pattern, you would have a reference to this node. So actually, I mean, in some sense, this is the top of this tree as well. So I'm kind of cheating. Maybe what we should do is that we should draw the arrows downwards, as with this tree, which would make it look like this instead, where again, the arrows are pointing downwards. So that's of course an equivalent representation of the decorator tree that we have here. So again, then the arrows are pointing downwards, and the base case node is found in the bottom, just as with the composite pattern. But then you can see that we have two different tree structures. So these are different ways of approaching the fact that they are somehow different. They are somehow sort of inverted. If you start to think about decorating the same thing multiple times, with multiple different decorators, if you actually actively try to use the decorator pattern to build a tree. Now clearly, again, another objection that you might have to this is that, of course, if we allow ourselves to do that in the decorator, I mean, I'm not saying allow as in like that would be breaking some kind of rule, but more as in that maybe we commonly wouldn't think about the decorator pattern as a tree, but if we start to think about it as a tree, right, in order just to discern the difference. If we allow ourselves to do that in the decorator, then I mean we could clearly allow ourselves to do that in the composite, which means that we would introduce other composite nodes that contain or wrap, in some sense, other components, which could be composite nodes or which could be leaves, which means that we suddenly end up in a scenario where we could build this, for example, or this. Which means that if you start to think about it, which means that the composite pattern can actually be used to build any tree that can be built using the decorator pattern. But the decorator pattern can't be used to build any tree that the composite pattern can be used to build. And of course, I mean, it's nothing strange. This is an inherent limitation of the fact that we've said that composites in the composite pattern can have references to multiple components, while when a decorator is decorating something, it can only decorate a single thing. Now, I'm not entirely sure of what the practical value of this excursion is, but maybe we could think about it this way. Firstly, I mean, of course, parentheses, I found it utterly interesting. But anyways, the concrete value we can draw from this is probably that if you have something that you think looks like a tree structure, probably you need the composite pattern. Even if you start to think about, wait, I can actually use Decorator Pattern to build trees. Decorator Pattern is not intended to be used to build trees. Decorator Pattern is intended to be used to attach additional behavior to objects. So you have a thing and you wrap it to attach additional behavior. That's what we tend to call a decorator. Whereas a composite, we actually use if we have something that we want to model as a tree structure. But as you can see from this short excursion of looking at the different trees, clearly they are very similar. So I mean, if we start to talk about a linked list, for example, right? A list that's built up of a node referencing another node, that's referencing another node, that's referencing another node. I mean, this looks like the prototypical decorator pattern use case or example. But maybe I would rather think of it as a composite because it's more about structure than it is about behavior. It's more about constructing a list. So it's not about matching up a bunch of different things in order to attach responsibility, which is more what the decorator pattern is for. But again, if it's a linked list, then every node only has a single reference to the next node. So it's not like a node has a reference to two nodes. So it's not actually a tree, which means maybe we wouldn't call it a hierarchical structure. But yeah, I mean, you could think of this as a hierarchical structure. So then again, we're back to intent. And maybe that's the easiest way to think about this. Decorator is about attaching responsibilities at runtime. You want to be flexible. You can think about it in terms of composition. You want to be able to compose different pieces of functionality. While the composite pattern is about constructing hierarchies or maybe even a list of things that you want to be able to perform some particular algorithm upon. But yeah, they're pretty similar, and I would say that the two key differentiating factors are A, the fact that we had another class in the decorator, and B, the fact that we only allow the decorator to wrap a single other component and not multiple components. Whereas we didn't have that class in composite, and whereas a composite can be a composite of multiple components. But that's it. I hope that makes sense and that you now feel that you have some understanding of the differences between the composite pattern and the decorator pattern. If you have any questions or comments, please do shoot them in the comments and we can discuss and dig down further into this. Beyond that, thank you super much for watching. Check out the description for links to both of the books. Remember to subscribe to stay tuned for more content like this. We have tons of patterns to go. Thank you again for watching, and I will see you in the next one.